Awesome. I think the recording has started, so welcome. Awesome. And Patrick, thank you for taking the time and presenting your project today. I think you all know the rules. We just discussed it briefly. So, whenever, Nassim, you're ready, go ahead. One of the things that I'm going to do is I'm going to run my clock. Uh, 8 minutes. I'll give you a warning for 2 minutes. Okay?
Okay. Okay.
Awesome. All right. Whenever you're ready, take over.
Uh, so my screen is visible, right?
Yes, I can see your screen.
Okay.
Yes.
Let me see if I can navigate through. Yeah. So the changes are seen, right?
Yes. Yes.
Okay. Okay. I'll start then. Hello, everyone. I'm Nasim Taj. Today I'll be presenting my project on machine learning driven design of iron to vanadium aluminum Heusler family thermoelectrics. The goal of this project is to use machine learning to predict and optimize the Seebeck coefficient in doped iron to vanadium aluminum family systems. I'll start with the motivation and behind this problem. So a little bit of background. Thermoelectrics are the materials that convert heat directly into electricity and vice versa. The key property we care about in thermoelectrics is the Seebeck coefficient. That is the ratio of the voltage difference generated by the temperature gradient. In Heusler alloys, like iron to vanadium aluminum, they are particularly interesting because their electronic structure is very tunable and their properties are very sensitive to doping. So by introducing dopants, we can change carrier concentration, band structure, scattering mechanisms. All of these directly influence Seebeck. So fundamentally, it is a material physics and data problem where we are trying to learn how composition maps to transport properties. And also another motivation is experimentally validating all the dopants is very expensive. So machine learning will help us through in the first place. In terms of literature review, previous work shows that doping in iron to vanadium aluminum has improved Seebeck. The studies are mostly experimental and they focus on a few dopants. Machine learning has been used in metals discovery very broadly, but there is no systematic machine learning framework that predicts the dopant-specific Seebeck behavior in iron to vanadium aluminum systems, especially with generalization across different dopants. That's the main problem this work addresses. So here's the framework I built. Here's the framework I built. So it has five main stages. First is the multi-host dataset that I built that includes the dopants, the concentration, the temperature with their specific Seebeck, the resistivity and thermal conductivity and all other data that I could find from the papers. Then I did feature engineering to reduce thousands of descriptors to 548 final descriptors. Then I did dimensionality reduction to use PCA and embedding to reduce dimensionality even further. And then I deployed different machine learning models like tree-based models, boosting models, also neural models, and most importantly, group k-fold for by dopants to finally design an optimized model that can predict outputs with optimal dopants and specific concentration. So for data, I started with 22,000 data features and then different filtering methods were applied by removing missing heavy features like whichever any features above 40% missing data was removed. I also removed low variance data, also highly correlated data was removed. So lastly, I was left with 548 final features. This ensures that model is not learning noise or redundant physics. Even 548 final features is very high dimensional. So later I applied PCA. So from the scree plot, also it can be seen that almost like 90% of the variance can be achieved from 20 PCs. But if we want to get 95% variance, we need 29 PCs. So I chose 29. This means the data is intrinsically low dimensional. However, we don't see clean clustering, which suggests that there is strong overlap between materials. Also, the relationship is non-linear, very complex. So we explore first unsupervised learning methods. First, from the elbow method and the silhouette, we can see that the k-means suggests optimal clusters are around 11, but the clusters are not cleanly separated, meaning materials behavior is continuous, not discrete. This also justifies flexible machine learning models that I have deployed later. Uh, in terms of supervised learning, I trained multiple models, including random forest, extra trees, gradient boosting, XGBoost, SVR, MLP, other linear models too. The best performing model I found was XGBoost with interpolation RMSE of 20.7 and R square of 0.93. Holdout RMSE was 21.18. And in terms of extrapolation, the gradient boosting performs the best with 48.5 of 5 RMSE. From the parity plot, we can see strong alignment with the between the prediction and the measured Seebeck. And from the residual plot, we can see that they are mostly centered around 0. And there are some outliers they occur due to dopant variability. So the model is very accurate with known chemistry, but extrapolation remains challenging. The most important features that I found were electronegativity, atomic radius, valence electrons, energy-related descriptors, and other energy-related descriptors. These directly control the band alignment and carrier concentration, also scattering that I discussed earlier. So from the predictions, we can find that from known or validated dopants, silicon, germanium, tin, and tantalum resulted in the highest Seebeck. Also, the model suggests some new candidates, including cerium, samarium, and dysporium, and some other risky but untested fallbacks, which are marked in red in the graph in the bottom right corner. So I also categorize the results in N-type and P-type classifiers. And from here, we can see it is 95% accurate for distinguishing between P and N types. And this can also be seen from the predicted versus actual plot that both in positive and negative range of Seebeck, it actually follows the red line very closely. And close to 0, it is very prone to errors, but other than that, it is very accurate. In terms of physical insight, we can clearly see from the previous graphs that the Seebeck distribution is bimodal. So in N-type, it is negative, and P-type is positive, which can easily be determined. Also, the main drivers are electronegativity, orbital radius, polarizability, and valence electrons. These actually control the band alignment, carrier concentration, the scattering strength, and there is no clean linear trend in dependence of concentration. And we know that the scattering is strong in this case, scattering is strong at lower concentration, and also the behavior is very saturational. So this is very competing because with high scattering, you get lower Seebeck, but with high scattering, we get higher Seebeck, but as carriers increase, we get low Seebeck. So this results in nonlinear and noisy relationship. Also, there is huge variation with the dopants and sites. So the local bonding environment changes with effective mass, scattering, and band structure. Among the limitations, the main limitation was the missing temperature ranges. So temperature is very fundamental for thermoelectrics, but the data set I gathered was not consistent with temperature fields. There are some missing mixes of low temperature and high temperature physics. So this may have impacted the results also. From pre-processing, the concentration I have sometimes from different papers are in fractions and sometimes in percentage. So this mixing can also result in some imputation. Also, the dopant space that I had is very sparse because there are many suggested dopants that are never seen in training. So this may violate the chemical stability, the solubility limits. Also, when I started the descriptor space, it was very high dimensional, like thousands of features, which then with PCA we reduced to only dominant modes. So the descriptors were redundant and correlated. So in conclusion, I developed a model physics-informed ML framework that predicted Seebeck in the iron to vanadium aluminum system. And I also successfully reduced the features from 22,000 to 548, which then I even addressed even more with PCA to reduce it to 29 pieces that address the curse of dimensionality. Also, I used group K fold to address overfitting uh, and achieved strong predictive performance of 20.7 with R square of 9.93 with XGBoost, and identified physical meaningful drivers like electronegativity, atomic radius, and valence electrons. Also generated actionable predictions. In future work, uh, these predictions can be experimentally validated for top dopants. Also, I would add DFT and band structure features to this to see how that changes the performance. Also improve the dopant generation, expand the data set, and standardize the conditions. Also explore co-doping strategies to see how that changes the behavior. Thank you so much. That's from all of my data that I had to share. Thank you so much for hearing to me. And if you have any questions, you're most welcome.
All right. Thank you, Nassim. Patrick, do you have questions?
Sure. Yeah. Can you go back to your unsupervised learning slide?
Yeah.
I just had one regarding that.
Yeah. Give me a minute.
Okay.
Yes, here. Yeah.
Okay. Because yeah, I know you mentioned a lot of a high volume of features that were helped boil down through like
Yes.
PCA and all that. One of the things that I was just curious on is that you had the K-mean silhouette going up to 11, but from the K-mean's elbow, it could have potentially been somewhere around like 6 or so. Do you think boiling it down to around there might have helped with the dimensionality reduction at all,
So,
determining groupings at all? Did you try that at all?
It's a very good question, and I also looked into that too because like k equals 11 is like very high in terms of clustering. So I started with looking at 6, so I didn't see anything. I also looked at 8, but it still was not well. Like you can see they are mixed in between. You can still see some clusters of like orange here. This is the best I found at k equal to 11. Otherwise, they are all mixed together at 6 or 8. So at 11, I found like you can see some clusters that are not mixed in between other clusters, but at lower dimensions, it was even like more mixed up. So that's why I chose 11. Also, like from the silhouette score, 11 has the highest silhouette score. So this resulted in me choosing the 11 as the clustering. But I didn't use this in the supervised learning because it is not obvious that there is actually proper clustering. So I just left it at that.
Okay, that was going to be my follow-on, but
yeah.
Okay.
Thank you so much for the question.
Yeah, thank you.
Thanks, Patrick. Talon, any questions?
Yeah, I actually had a few questions and some comments. So
Okay.
you started off just discussing what the Seebeck coefficient exactly measures and that there are no like machine learning models currently available,
Yes.
like given for the structure.
Yeah.
Are there certain limitations for running experiments for measuring these? Like, what's the need for doing machine learning?
So the first thing is iron to vanadium aluminum is like one of the most well-studied system in Heuslers. So like all the uh, like what can I say in terms of costs, all the cheap dopants that you can think of has already been used to determine like what is the highest Seebeck or what is the phase change behavior that we can get from this system. But if we look at even like systems that are like dopant systems that are very scarce or very hard to get hands on, there are very limited data on this system. So the main idea that I had in mind was to actually see if those dopants that has been used in different systems, not in this one, can result in even higher Seebeck. So if you look at my predictions later on, here. So the new candidates that it suggested are very uncommon, like cerium, samarium, and dysprosium. So these are like very scarce and very expensive dopants. So in terms of like the validated ones like tin, silicon, germanium, tantalum, these are very available and the data was also available. So I wanted to see if in exclusive systems this can result in even higher Seebeck, or is it actually worth looking into them? That's why.
Okay, thank you. Now I just had two more questions, a few
Yeah, sure,
comments. So,
sure.
you said that for selecting the number of significant principal components, you stopped around like 29, and that captured
Yes,
95% of the total
yes.
explainable variance. What was your rationale for choosing like the 29? Was it just you had a cutoff at 95, or
Yeah, I chose the cutoff at 95. That's just it.
okay? And then you presented some R squared results. Is that for
Yes.
training or testing R squared?
So I didn't show you the entire R square values that I have. This is the entire table that I had. So the values I showed you is for the test values.
Okay. Yeah. It'd be good, and I guess this will segue into my comments, but whenever you do present an R squared, it'd be good to distinguish whether it is training or testing
Oh,
along with the same
yes.
like error metrics.
Yeah, thank you
Um,
so much for that. Yeah, I should have mentioned.
yeah. And I liked your connections back to the core physics at the end of like why certain features probably would have been most important. But I think on one of your final slides you said that you had like a physics informed model or something. I would just or machine learning framework. I would just be careful in using physics informed because that implies that you actually incorporate the physics in a loss function, like what's being used to
Okay.
optimize these. So even though the descriptors are all essentially rooted in physics, like why you picked them, I'll just be careful in saying physics informed because that's like a pretty popular term
Yeah.
in machine learning.
Yeah, I got it. Yeah, thank you so much for that. Yeah, thank you.
Yeah, that's all my questions. Thank you.
All right, so I have a few comments, Nassim. Number one is, I think the broader, I want to set a common table for everybody. So I would, I think it's good that you tried different things. But I would, at the end of the day, in the final report, please only include the results of the techniques discussed in the class.
Yeah.
We did not discuss UMAP, we did not discuss XGBoost and so on. So I would say stay away from that. MLP,
So, Professor,
SV,
yeah,
SVR,
so
right,
should I not include so I got the best result from XGBoost. I think you mentioned XGBoost once in one
right.
class, I think.
I would
So,
say I would start with gradient boosting because
okay.
XGBoost is a little different and we haven't discussed the hypothesis functions and so on.
Yes,
So
yes.
I would stay away from that. I mean, you can develop it further, right? So, I mean,
Yeah,
for this class to be responsive to this course, I wouldn't include XGBoost,
got it.
right? I
Okay, so
wouldn't include MLP, I wouldn't include SVR, right? So
okay,
things
okay.
that we discussed in the class, I think that is more than sufficient,
Yeah, so
right?
I tried, yes, Professor. So actually, I have tried all of those too. So I will
Sure.
address those, but they resulted in very bad. Like when I tried Ridge regression or Lasso is performing a little better, but when I tried Ridge, it was giving me R square into negative.
Sure.
So yeah,
Right.
so that's why I didn't keep them in the presentation. But yeah, I'll address them that's
I would I would
properly.
ra I would rather be curious to see why Ridge did not perform well and what are your strategies to improve Ridge rather than trying more complicated techniques,
Got it. Got it.
right? So, I mean, the random forest that you show me seems interesting here. I mean, 0.85, 0.72 is a much, I would trust the generalizability of random forest more than XGBoost in this case. So, at
Okay.
the same time, uh, what is not clear is how did you do the hyperparameter optimization and so on. So I would rather spend more time on, those rigorous details than list of other techniques, right? So
Yes.
including UMAP. I don't want to see UMAP because I think we didn't discuss UMAP at all in this class. So that's the first comment. Uh, Again, we did not discuss classifiers, so I wouldn't include classifiers in your final result, in your final report.
Okay.
So stick to regression. Uh, what was not clear to me was how many data points did you have in the data set?
So let me just go here. So I briefly mentioned it here, but maybe I didn't say the number out loud. So I had in total 1,897 rows
Okay.
And from there, 70% were iron, vanadium, aluminum, and 4% of each of these and some other samples.
Okay.
So, like it would be around like almost 1,400 rows for iron, vanadium, and
Okay. All right. So maybe
yeah.
making that clear would help.
Yes, I should have mentioned. Oh, so I should have. Yeah, I think I removed the numbers later. I just put the percentage here. Yeah. Okay, I'll
Right.
mention that.
Okay. I think I have other questions, but not that important for this class, so I'll stop right here.
Okay, Professor. Yeah, I am planning to actually move forward with this project even further. So
Sure.
hopefully I'll be in touch with you.
No worries. Yes, we can build on this. Yes.
Yeah.